In this video, I'm going to show you how you can learn about recursion by exploring existing recursive methods using the JGrasp visualizer. And here I created a short program that creates a BST from ALX4, fills it with some characters, and then we are going to look at the method sealing. So before I step into the debugger and open the JGrasp visualizer, I just want to have a brief look at the BST. That's a nice feature of ALX4 jar. It comes with the code, so if I right click and say open declaration, it's going to open the code of BST right here. One thing I want to point out is the class node. So we introduced already nodes when we had the singly linked list. In that case, a node had an item and then a pointer to the next node. In case of a binary search tree, we can have two children. So you can see here the left and the right node. And also we don't call it item, we call it key, because the binary search trees are designed to provide a data structure that allows us to find keys efficiently, add them efficiently, remove them efficiently, but most commonly find them efficiently. So the key is associated with a value. This could be, for example, a word in a dictionary associated with a meaning, a student ID associated with a student record. So for now, the BST focuses on the keys, how we can store them in an efficient way. Now, BST itself isn't that efficient because it can be unbalanced. What really will make it much more efficient is the balanced BST that we will cover, which is going to be the left-leaning grep-like tree. But for now, we just have a BST, and we are going to look at sealing. So here I say sealing, and you can see when we have the method sealing here, it starts with a public method that asks the user for minimal input, just which key are you interested in, and the method sealing will return the smallest key in the symbol table that is either greater than or equal to the key. And that is a common pattern. So here we call the public method with the minimal required input from the user. And this method sets up the private recursive method. So here we have the private recursive method that requires not only the key, but also a node. That node, it's just called X here, but it is really the root of the current subtree where we're looking. So that is the recursive method that we're going to explore. So let's just get back here to our demo class and get started. I'm going to set myself a breakpoint. Actually, I did already. And I'm going to step into my debugger. I'm going to switch to debug view. And so here I can see we have already the symbol table. We created it, we filled it. By the way, the keys are those uppercase letters. The value that I chose as an associated value is just a lowercase version. That was totally arbitrary. I just thought it was a reasonable idea for this demo here. So here is my ST. Now I just see a little square. What I'm going to do is I'm opening that. I'm going to click this icon here with the red triangle, and it gives me something like a canvas, a viewer canvas, and I can drag my symbol table on that viewer canvas. So it takes a little bit of an adjustment the first time, but the nice thing is once I have my viewer canvas set up, I can just keep reusing it multiple times. So I want to make sure it's you can see all of the tree here. So now we have the whole tree available. And the other thing I would like to show is the key, because here we are passing M as our key. I'm going to add that in a minute. So here is my tree. Here is my tree, my symbol table, the binary search tree with the root P. That was the first element we entered. Now I want to have a look at the method sealing. This is the public method sealing. It just provided, that just required a single element, the key we're looking for. So we look for a key that is either M or the next bigger element to M. So if you look in this key, you can find there is M is not part of my tree. The next bigger element is going to be N. So that's what I hope to be found. So here I'm going to step into my method, and what I find is it opens class character. It opens class character because we passed as an argument a character, a primitive type character. Now this is autoboxing. Automatically it creates a uppercase character object out of it. I don't want to watch how that is done, so I can just step out of it again. That brings me back because what I'm interested in is the method ceiling. So I say, well, let's step in that again. And there we are. This is the method ceiling. So it says, well, if the key we provided is null, then it would throw an illegal argument exception. Let's just make sure we have the right key. That should be M. So here, when I look at my key, it gives me a square. I'm going to drag that over here and I can see my key is M. And I'm going to bring back enough so you can see it. And sometimes I might cut off a little bit on the side, but we'll be fine. So here we are. The key is M. That is not null. So it's not going to throw an exception. The symbol table is not empty, so we're not going to throw an exception. And now we're ready to call ceiling, which is the private recursive method. Now, before I call ceiling, I just want you to appreciate that each of those is a node. So you can see here, the node has the key in blue. It has an associated value. That is the lowercase version in my case. And then it has two children, the left and the right child, which are nodes themselves, or sometimes they're null. That means that's a leaf. If there's no child, then the node is called a leaf. So right here, we are considering the whole tree, the whole symbol table. You can hear me refer of it either way because this symbol table is a tree. And we're going to look for the key that is either M or the smallest key greater to M. That means ceiling. So let's step into it. Here we are, we're stepping into it. As we step into it, the first parameter, which was passed as the root, is called X in this context. So here it says X, it points to the root. First step here, we check whether X is null. That is not the case. X, in our case, is this node with P. So we are stepping over it, we're making a comparison, we're comparing whether our key, M, is greater, smaller, equal to the key of the node, which is P. M is less than P. So the next check here is going to return false because the comparison is not 0. That would only be the case if M and P were equal. Now here it checks is the result of the compare to method negative. That is the case because M was less than P. So we're going to step into that one. So here we are stepping into this branch of the if statement and we are calling ceiling again. But this time we call it on the left subtree. We call it on the left subtree because we're confident M can only be in the left subtree because M is less than P. And so potentially the smallest number that is greater than M could be P, but definitely it will not be on the right side. So we're checking the left subtree. Let's hop into it. And as we do, you can see X is pointing to F. Why? Because F is the root of the left subtree. And again, we're going to check, is that root of the subtree null? That is not the case. And then we compare the key M with the key of the current root of the subtree. This is F. So M is greater than F. So we know for sure it's not going to be on the left subtree anywhere. So let's just walk through this through the code here. We are checking, is the comparison 0? That means was M equal to F? That's of course not the case. Is the compare is negative, was m less than f? That's not the case either. And then we're checking, we're calling ceiling. At this point, we know m was greater than f. We saw this right away. We're calling ceiling again. This time we call it with the root of the right subtree, because that's where we're going to look. How do I know? It says x dot right. That is the right child of my current root of the root of my current subtree. So here we call ceiling. We step into it. Now it points to j. We're working on that subtree here. We're doing the same thing again. We're checking, well, is the root of this subtree, which is j, null? That is not the case. We're going to compare m with j. M is greater than j. So we are checking, was m and j equal? That is not the case. We're checking, was m less than j? That was not the case. So we are going to explore the right subtree of j. We are calling it again, this time with the right child of j, which happens to be n. So there we go. We are hopping into it. Now my x points to n. That is the subtree we are exploring. We are checking, is the root of this subtree null? That was not the case. So we compare m with n. Now m is less than n. There is the possibility that maybe in this left subtree there could still be m. So here we are checking, is m equal to n? Not the case. Is m smaller than n? Yes, that is the case. So we have to explore this subtree here. So we are stepping into it. You can see now we're exploring this subtree, L. And again, same spiel happening. Is my node with L null? Not the case. We are comparing m with L. M is greater than L. So it's not equal, it's not less, it's greater. So we're calling ceiling with the right child of x. Now if you look here, the right child of this node here, that is null. So we're going to call the ceiling method with null. Let's look how this looks here. So here we are checking, is x null? This time we actually did pass null. You can see that here. And what are we going to do? We're going to return null. So we're returning null. That brings us back where we left off before, when we were exploring the subtree with L as a root. But at that point, L, when we were exploring L, we were just calling the ceiling, and this was it. So as we continue, it brings us back to the next higher level when we were calling ceiling on the subtree where n was the root. So here we called ceiling, but this time we were assigning the result to node. So we are assigning null to the node. So at this point it's checking, it says, hey, is t different from null? That is not the case, because t is null. We did not find m. So in this case, this if statement is not going to be triggered because the condition is false. It brings us in the else branch. It says, well, since we did not find m, that means n is the smallest element bigger than m. It's going to return x. My x at that point is n. So I can keep going. So it's going to return ceiling from the right child, and it's going to assign it to d. In this case, the t was not null, so it's going to return t. And we are back in our original public method. Now the node we have been propagating up is the node n that was identified. So here it is going to check. It says, well, is n null? That is not the case. So it's going to return the key of that node with n, and the key is n. So it says, well, n is the key that is the smallest key greater or equal to m. It's going to bring that back, and now at this point when it's going to be assigned to ceiling, and when we print it, it tells us ceiling of m. Now notice this is just a label. That's how we would call it in code. That's just a label, the ceiling of m. That is n. That is the smallest element or the smallest key greater or equal to n. Hope that helped.